This lesson is from 3.2, working with derivatives, and basically we're looking at the graphs of derivatives. So I want to start with Desmos here. I want you to understand what's going on. So we have a few graphs here. Let me get my mouse connected. So this red graph that you see, that is the original function. Actually, let me change that to, can I change that to black? I think that'll be better. Uh-oh, where did it go? There it is. I want to do my tangent line in red instead. I think that'll be better. What's it doing here? It's doing weird stuff. There we go. And I want to graph my derivative in red. So let me make this solid red. So the red graph is the derivative. The red dashed line is the tangent line. And the black is the original curve. So here's what I want you to notice. Let me move that to the top right there. So right at the top, you'll notice the slope is about 0. I can't get it right there, but it's about 0. So when I graph that graph at that point, the derivative should be 0. That's why the actual red graph, which is the derivative, is 0 right there. Now there's another place where it's 0. So here it becomes negative, big negative. It starts to flatten out, and it's 0 right around there. That's why the red graph is 0 at that point. Now, what I want you to also notice, so in this region, from here to the left, the derivative is positive. The slope of the tangent line is positive. As I move right, the slope it continues to be positive, but it becomes smaller and smaller and smaller, and then it approaches 0 right there. So the derivative, which is the slope of the tangent line, starts out really big. That's why we have the dot way up here. And as the slope flattens out, the derivative gets smaller. That's why you see the derivative dropping. And it's going to drop all the way. And if we get to that top point where it's flat, it'll drop to 0. So since the slopes are positive in this region, the derivatives better be positive. And since its slope of the tangent line is bigger here than here, the derivative is bigger. Now, in the region from here to here, hopefully you can see that the slopes are negative. 0 there, 0 there. In between, it's always negative. The steepest it gets is right there, that area. That's the steepest negative slope. So that is going to be the biggest negative value. So you go from a 0 slope, small negative. That's why we're moving down on the derivative graph. Bigger negative, bigger, bigger, biggest negative. It starts to flatten out here. So therefore now it's going to approach 0. And now the slope's back to 0. And what you should notice in this region, the slope gets steeper and steeper and steeper. Therefore, the derivative gets bigger and bigger and bigger, and it's positive. The slope in this region is positive, so the derivative just keeps moving up as we move to the right. So that's what's happening. That's how you kind of graph the derivative. What I would look for the points where the slope is 0, and then you plot that 0 point. Look for the other one where it's 0. Plot that 0 point. Notice the slopes are positive here, so you know the graph should be on top. In this region, the slopes are negative, therefore it should be below the x-axis. Here the slopes are positive, so it's above. And the steeper it is, the bigger the value. Let me jump back to this. Let's try to make some connections with this part. Let me start with a different one instead. Here we go. So I've drawn some tangent lines. And you'll notice at this point here, and this point here, the tangent lines are all horizontal, meaning the slope is 0. So I'm going to graph the function in blue, y prime, which is g prime of x. So here, the slope is 0, so my derivative at that point will be 0. Here, the slope is 0, so when I graph my derivative, it will be 0. Here, the slope is 0, so when I graph, it's going to be 0. Now here, all the slopes are positive. So therefore, my graph is going to be above the x-axis where positive values lie. And this is a big positive, smaller positive, 0. So the graph is going to start with big positive, smaller positive, 0. So it's going to be decreasing. And again, because the slopes are going from big, smaller, 0. Big, smaller, 0. Now in this region, here to here, the tangent lines have a negative slope. So it's going to go from 0, small negative, bigger negative, smaller negative, 0. So the biggest negative slope is around there. So the graph will be biggest negative there. So it's going to go from, again, small, 0. Let me erase that. I didn't mean to do that. It's going to go from 0, small negative, bigger negative, smaller negative, 0. So I go from 0, small negative, big negative, smaller negative, 0. In this region here, all the slopes are positive. You start with 0, bigger, biggest, smaller, 0. So it's positive. So above the x-axis, the steepest slope is there. So I'm going to get bigger, biggest, smaller, 0. Again, if you follow that, 0, bigger slope, biggest slope, smaller slope, 0. So we start with a 0 slope, bigger slope, biggest, smaller, 0, if you follow that pattern. And then if you look in this region, all the slopes are negative. And it starts with 0, a small negative, bigger negative, bigger negative. So they're getting bigger in the negative direction. So when I graph this, it just keeps getting bigger in the negative direction. So that's the graph of that. Now, on this next one, you could pause and try this on your own, and then I will show you what's going on. So now that you've tried this, I will pick my 0 slopes. I know there's a 0 slope right there. So at that point, I make my derivative 0. That's that dot. Now let's look at the slopes. This is a really big negative slope. Not as big negative, not as big negative, not as big negative, then 0. So it starts with a big negative slope, and it becomes less and less steep, and I go that way. Now this region here, let's watch. This is a 0, small positive, bigger positive, bigger positive, bigger positive. It just keeps getting bigger and bigger, so my derivatives keep getting bigger and bigger. Now let's look at this region. Big negative slope. Not as big negative, not as big negative, not as big negative. And here it's a small negative, and it's approaching 0 as I move to the right. So it starts with a big negative, not as big negative, approaching 0. So I start with a big negative, and it becomes less and less negative and approaches 0. So that's the graph on the right side. Then on the left side, you will notice negative slope, negative slope, negative slope, negative slope, negative. They're all negative, but it's almost 0 here, and it becomes bigger and bigger negative as I move right. So it's almost 0 here and bigger as I move to the right. So there is the graph of the derivative of this function. So what is going on here? This is a theorem you have to know. And this will be summarized in a second here, but if f is differentiable at a point, differentiable means the derivative exists. If the derivative exists at a point, then the function must be continuous. So if that's true, the contrapositive says, if the function is not continuous at a point, then it will not be differentiable at that point, or the derivative will not exist at that point. So not continuous, not differentiable. So here are the 3 things you have to know if we ever take a quiz. This will be a common theme on tests. When is a function not differentiable? You have 3 situations. Not continuous, then it will not be differentiable. If it has a corner or a sharp point, it will not be differentiable. Or if the tangent line is vertical. And I'll give you an example of all these. Here, we have a discontinuity. Therefore, the function is not differentiable at A. Everywhere else we're good, but at the discontinuity, it's not differentiable. Here you'll notice we have a sharp point. So that's one reason why the derivative doesn't exist. And on top of that, the tangent line is vertical, but it is a sharp point, and I will emphasize that in a second here. And the next one, look at that tangent line. It's vertical. The slope of a tangent line is undefined. You should know that. Slope of a horizontal line, 0. Slope of a vertical line, undefined. Since the derivative is the slope of a tangent line, and if this slope is undefined, then the derivative is undefined when the tangent line is vertical. Now let me explain why sharp points are bad at a corner or a sharp point. The derivative is a limit of the slopes. And you know, for a limit to exist, the left hand and the right hand limit must be the same. So the slopes approaching from the right must be the same as the slopes approaching from the left. They must be equal to each other. So for an example, if we take a look at this point here, and if you find the slopes of the tangent lines as we approach there, from that side and the slopes from that side, the slopes will be the same where they meet. But if you take a look at this point down here, you're going to have a different situation. If you take the slope of the tangent lines approaching that, as we get closer, those slopes are positive. As we approach from this side, those slopes are negative. Where they meet, the slopes are not the same on both sides. If the limit of each side is different, then the limit doesn't exist. Since this limit is the definition of the derivative will not exist there. All right? So we're looking at this problem. I will walk through this with you. If we were going to graph the derivative of this, this is what it would look like. Here, the slope of this line is constant. It's always the same slope. Any point you pick, the slope's the same. That means the derivative will be a constant and it's a positive slope. So therefore, we draw this line and it's always the same value. It's a constant value. The slope does not change, so the derivative is the same. Here we have a discontinuity. If a function is not continuous, the derivative doesn't exist. So when you graph the derivative, you make sure you have holes there because the derivative shouldn't exist. Now, from here to here, the slopes get bigger and bigger negative. So from -2 to 1, or 0, the slopes get bigger and bigger negative, or the derivative gets bigger and bigger negative. All right, there's a sharp point there, so the derivative will not exist. In this region, all the slopes are positive, and we start with a very steep positive slope, smaller positive, 0. So you start with a big derivative, it gets smaller and smaller and smaller, 0. But at 2, there's a discontinuity, therefore the derivative doesn't exist, so when you graph the derivative, you put a hole showing it doesn't exist there. Now in this region, the slopes go from 0 to bigger and bigger and negative. So you start from 0 and you go bigger and bigger and negative as you move right. So that is the graph of this function. And that is the end of this video. That is tips on how to graph functions. And just to summarize, I want to say this. I don't know if I did this or not. I would first look for the 0 points, plot the 0 points. Then I look for where the slopes are positive and make sure I'm above the x-axis there. Then I look for where the slopes are negative and make sure that my derivatives are negative there. Then where it's positive, and then I make sure my derivative is positive there. And where the slopes are negative and make sure my derivatives are negative in that region. All right, that's it. I'll talk to you guys later.